Okay, we have seen amplifiers using the Mosfet. So if I just write all those Mosfet amplifiers, so this is SES amplifier with R1, R2 and RD as the resistive load. So this is VDD, this is ground, CC, this is Vin, this is where you measure V0, this is M1. And if I write this is my okay, let us start with this. Now whenever we want to get the output, so we know that output is given by minus V in into Gm into RD, Gm into RD. So this Gm into RD is the one which decides the output amplitude for a given input. Suppose if you want to increase the gain of the amplifier, so we know that AV is now given by minus Gm into RD. If you want to increase the gain of the amplifier, either you have to increase the value of GM or you have to increase the value of RD. So how do you increase GM? So we know that GM is given by under root of 2 ID KP into W by L. So this is how you can increase the value of GM. So in which, so there is a ID component. So where if you increase this ID, so we have a DC voltage corresponding to this at drain as VD, which is nothing but VD is equal to VDD minus ID into RD. ID into RD. So now let us try to find out the impact of increasing the gain by increasing either RD or GM. If you increase GM or if you increase RD. So how can you increase GM? So GM can be increased by increasing ID. And ID can be increased by using larger VGS or larger W bell and so on. So now whenever this ID increases, the AB will increase. Whenever this RD increases, AB will certainly increase. But let us not only have a look at the increase of your GM or RD. Let us see the impact of that increase in GM or increase of RD on the VD value. See now, if you increase GM, the ID will increase. If you increase RD, this RD will increase. So either this will increase or this will increase if you want to increase GM or if you increase RD. In other words, if you want to increase AV, the gain of the amplifier, this drop will increase. This drop will increase. If this drop increases, so it's like this is a constant value, VDD minus something you are subtracting. Whenever you are subtracting something from a constant value, naturally the resultant is keep on reducing. So whenever you actually increase the value of uh, if you want to increase the value of AV, so VD is keep reducing. So VD is keep reducing. What is the problem if your VD is keep reducing? Suppose if VD is keep reducing and if it comes less than VDS sat, so then this MOSFET is not in linear region. So if the MOSFET is not in linear region, what are equations that we have used for calculation, that is Gm into Rd, because we got this expression of this value of Gm into Rd from this small signal model. So this is our small signal model through which we got the expression of Gm into Rd. So in this small signal model, we have replaced the MOSFET by this. So this is possible only if the MOSFET is operating in saturation region. So what all GM expression you got, which is nothing but under root of 2 ID KP W bell. This ID is actually ID sat. ID sat. If the MOSFET is not in saturation, then this GM is not valid. This entire equivalent circuit is not valid. So then this is also not valid. So this is valid only if the MOSFET is operating in saturation region. That means VD has to be greater than VDS sat. VDS sat. So in order to increase gain, if the increment of GM or RD, if it makes UPS on. So now with the increase, in order to increase AV, either increasing GM or RD may put this MOSFET in linear region. So in such case, so it is not possible to get the amplification at all. So what the point now is, using resistive loads RD, so it is not possible to get larger gains. So what we have to do, we have to replace this RD by something which will have a larger resistance but doesn't consume voltage. So that's what we will use MOSFET itself as the load to get larger gains. So that's what is the analysis. Now what we'll do is we'll just write the same circuit. Now, whenever you are analyzing the MOSFET as a load, we have to always consider lambda non-zero. So before of course, lambda should be non-zero. When lambda is non-zero for this, so then this becomes RD parallel R naught. So this is RD parallel R naught, and of course this is again RD parallel R naught. So now let me replace that resistor RD by a MOSFET. Now, before we start using in place of RD and MOSFET, so let us try to understand what is the resistance looking from drain and source under different conditions. I will just summarize. So the detailed analysis you just look at in another existing videos. If I AC ground this, if I AC ground this, upon AC grounding the gate and thank you. If you're grounding, of course, when I say grounding, this should be AC ground. AC ground. This is AC grounded, and source is also AC grounded. If you look from the drain, the resistance is R naught, where R naught is given by 1 over ID into lambda. On the same lines, if this is AC grounded and if the drain is also AC grounded, if you look from the source, then the resistance is 1 over GM in parallel with R naught. This is true for both NMOS. This is actually NMOS transistor. This is also NMOS transistor. Suppose if I do it for a PMOS transistor. So this is a PMOS transistor. This is source. You ground the source. Of course, when I say ground, AC grounded. This is also AC grounded. If you look from the drain, it is R naught. Again, consider a PMOS transistor. This is your source. Look into the source. This is AC grounded. This is also AC grounded. So now this resistance is 1 over GM in parallel with R naught. Now you consider a case where you have this is the source is AC grounded. This gate and drain are shorted. If you look from here, it is now again 1 over GM parallel with R naught. This is a NMOS transistor. Source is AC grounded. Gate and drain are shorted. If you look from this, the MOSFET is in saturation region. The resistance looking into the drain is 1 over GM parallel with R naught. Same is true for a PMOS transistor also. This is now AC grounded. I'll short gate and drain. I'll look into the drain. It is 1 over GM parallel with R naught. These are different combinations. Other combinations would be, you consider a NMOS transistor. This is connected with some RS AC ground this. If you look from here, the resistance is R0 plus RS into 1 plus GM R0. So this is the overall resistance looking into the drain if source is connected to ground through RS. So this is the resistance. So now I will look for another possibility where you have, now this is source, now this is your drain. If the drain is connected to ground through some RD, now what is the resistance looking towards the source? When you are looking towards the source, the resistance now is, the resistance is 1 over Gm plus Rd divided by 1 plus Gm into R0. Gm into R0. So this is true for both NMOS as well as PMOS transistors. So just carefully have a look at it. This is AC grounded. The source is connected to ground through RS. The drain is connected to ground through RD. The resistance looking into drain is R0 plus RS into so and so. This is fine. And of course, this can be a MOSFET also. This can be a MOSFET also. Then this RD and RS will change according to the MOSFET whatever you have. Fine. So this is MOSFET as, this is MOSFET as load. This is MOSFET as load. So these are different combinations. Of course, you can end up with n number of combinations are possible. So let us use one of the load for CS amplifier. Let us do it for all different loads. Now let me just take a typical CS amplifier. This is my load. This is my CS amplifier. This is V in. I'll ground it. This is VDD. I'll say this is R load. Or let me say it simply say it as load. This is my load. This is V0. This is my CS amplifier. This is assume it as M1. So now what is AV? AV is nothing but let me say it as R load itself. Some resistance, not resistance. There is a load that is available. So AV is now equal to I can rewrite. Okay, what I'll do now is okay. This is the, what is this? What are the possible circuits you can think of? The circuit I can think of is, first is this. This is V in. This is let me say if it is a resistive load. So this is M1. This is V0. This is RD. This is VDD. So what is V0 by V in? Here it is minus Gm into RD parallel R0. RD parallel R0. And if it is some other load, you ground it. This is V in. I'll have some bias voltage. This is VDD. This is my output point. Assume that this is NMOS transistor. This is M2 PMOS transistor. The gain of this will be VAB is equal to minus GM into, what is this now? The looking down is R01, looking up is R02. So in place of RD, okay, let me say this as R01. In place of RD, you have R02. The R01 is as it is. If you want to find what is R out of this, R out of this is this resistance divided, of course, in parallel with this. So it is like R up in parallel with R down. So R up is RD, R down is R not down. So of course over here input impedance is infinite. So what is R out here? R out is R up is R not 2 R down is R0 1. R0. So these are all CS amplifier different loads, resistive load, active load. And what is the other possibility? Other possibility can be this. I can have this is V in, this is now, I can have this as VDD, can have it as VDD, this is V0, I can have it as VB. Assume that this is also a NMOS transistor, this is M2. So now what is gain? So AV is nothing but minus GM1 into, is actually GM1, this is also GM1. So minus GM1 multiplied by the resistance looking down is R01 parallel with resistance looking up is 1 over GM2 in parallel with R02. So this is my gain. So what is R out? It is resistance looking up is 1 over GM2 in parallel with R02, and that in parallel with looking down is R01. R01. So this is R out. What is R in? R in is still infinity. R in is infinity. Now, what is, so let us think of some other different load. So load can be this, something like this. So this may be not. This is, assume that this is VB1, this is VB2, this is, okay, assume that this is VDD, assume that this is NMOS, this is also, sorry, both are PMOS and this is NMOS V in. This is a CS amplifier. So let us name it as M1, M2, M3. So what is gain now? It is minus GM1 into R01 parallel with. So what is the resistance looking up here? It is R02 plus 1 plus GM2 R02 into R03. So this is what is the resistance looking up here. The resistance looking up here is R02 plus 1 over GM2 R02 into R03. So what is looking down? It is R01. So this itself will be your R out also. So this is your R out. This is R out also. So what we are writing this? So this is R out. What is R in? R in is infinity. So this is AV for this circuit. So these are all different configurations of CS amplifier. Of course, you can think of CG amplifier, CD amplifier, replace that resistor by active load, maybe of course you can have different combinations of so because this is your CD amplifier, correct? This is V0, this is V in, this is VDD, and this is M1, this is RD. What is the expression? So for AV it is GM RD parallel R01 divided by 1 plus GM1, okay, sorry, this is RS, let me name because it's connected to source, RS parallel R01. So now what is R out? R out is, so this is the resistance looking up, which is 1 over GM, 1 over GM1 parallel with R01 is the resistance looking up, the resistance looking down is RS. So this is my R out. This is one CD amplifier with resistive load amplifier with lambda non-zero, So now if you have another, so now you can see this is again VDD. I can just use this as a bias voltage. Here it is V in. If you measure V0 here, this is M2, this is M1. Then what is AV? AV is given by GM1 into what is this is R02. R02 is in place of RS, and you have parallel R01 as it is, divided by what is this? This is 1 plus GM1 R02 in parallel with R01. So what is R out? R out is, so what is the resistance looking up? It is 1 over GM1 parallel with R01. So what is the resistance looking down? It is R02. This is out. So what is the other possibility? Other possibility can be, you can have something like this. This is V in. This is some bias voltage. If it is a PMOS transistor, this is VDD, this is V0, this is M1, this is M2. So what is AV here for this? AV here for this is GM1 into 1 over GM2 parallel with R02 is in place of RS. Of course, R02 remains same as it is, divided by 1 plus 1 over, GM1 multiplied by 1 over GM2 parallel with R02, that is in parallel with R0, R01, R01. So this is, so what is R out here? So in place of RS, here you had R02. In place of RS, here you have 1 over GM2 parallel with R02. Otherwise all other terms are same. What is R out? R out is resistance looking up is 1 over GM1 parallel with R01. That is again in parallel with 1 over GM2 in parallel with R0. So you'll have a very small resistance. You'll have a very small resistance. So Rn is again, of course, you can treat it as infinite. So in all these cases, lambda is non-zero. You'll have some typical value. So these are all CD amplifiers. Of course, you can think of CG amplifier also. Okay, let me just look for CG amplifier. So if I just, okay, let me just write a very simple CG amplifier, which is something like this. V in, this is VB, this is V0, so on so. This is RD, this is VD. So expression for AV is GM into RD. If lambda is non-zero, then this is R0, parallel with R0. So then this reduces to, suppose if this load is an active load. So if it is an active load, what will happen? Sorry. If it's an active load, the load can be something like this. This is your, both are bias voltages, VB1, VB2, this is M1, assume that this is M2, this is VDD, here you are measuring V0, this is your V in here. So what is AV for this? AV for this is GM1 into, in place of RD you have R02, because this is R01 as it is. What was the output impedance here? The output impedance here was RD in parallel with R01. What is the output impedance here? The output impedance here is R02 in parallel with R01. The, of course, input impedance is now, okay, what is Rin? So Rin now is equal to 1 over GM1 plus of this is R02 divided by 1 plus GM1 R01. So this is the input impedance. Here Rin would be equal to 1 over GM, of course this is 1 over GM1 parallel with R0, okay, that is very minimal. So it is 1 over GM1 plus RD divided by 1 plus GM1 R0 GM1 R0. So in place of RD you have R0. So this CG amplifier will have a very low input impedance. So this is basically used as a current amplifier. So now, of course, this can be a NMOS transistor also. You can just think of having this. This is VB. This is also some bias voltage VB1, VB2. This is VDD. It can be this. You can have this. So this is your input here. So this is your V0. This is M1. This is M2. So what is AB? It is GM1 into what is the resistance looking up here? It is 1 over GM2 in parallel with R02 parallel with R01 is your gain. R out is the resistance looking down is R01, looking up is 1 over GM2 in parallel with R02, and of course R in is 1 over GM1 plus 1 over GM2 parallel with R02 divided by 1 plus GM1 R02. These are the expression for gain R in, R out and R in for this CG amplifier. This is also CG amplifier. These are different varieties of CG amplifiers. And of course, given a problem of certain dimensions, so whatever current, if you know the dimensions current and VGS, you can easily find out GM R0. So once you know GM R0, so then you can easily find what is the expression for gain, and because in all the expressions you need to know what is just GM and R0 for a given MOSFET. So if the dimension is given, if the currents are given, so then it's very easy to find the specific values of gain and R in, R out. So depending on the value of lambda, So that way you can able to comfortably do all this analysis. Okay, now we will also see another amplifier, which is a Cascode amplifier, which is nothing but so Cascode, which will have SCS amplifier. So this is SCS amplifier with open circuited load, to which you'll apply, you will connect a CG amplifier. So this is now a bias voltage. So this output will become input for the CG amplifier. Let me say it as this is an open circuit. This is an open circuit. If you say this is V01 and if this is V02, what is V01? So V01 is actually the resistance looking up now is infinity. So why the resistance looking up now is infinity is, so let me say it as M1, M2. The resistance looking up over here is 1 over GM2 plus, so what is the resistance over here? It's infinity divided by 1 plus GM2 R02. So this is actually infinity. So that's how this resistance looking up is infinity. So once it is infinity, so then what is V01? V01 by V in is nothing but minus GM1 into R01 parallel with infinity. So I will call this as AV01, which is this, and what is A02. Now this is an open circuited thing, so the input for this is, it's like, okay, V02 by V01, which is nothing but GM2 multiplied by R02 parallel with infinity. So why this is infinity is because it's open circuit. Why this is infinity is, even though it's not open circuited, you'll have a gain of, so this is an open circuit, but this is not an open circuit, but it looks like infinity. It looks like infinity. So that's why open circuited is called as A0, with some connection is called as AV0. So what is the overall gain? So overall gain is V02 by V in. So I can write it as V02 by V01, V01 by V in 1. So this and this. So I know what is this. So V01 by V in 1 is nothing but AV01 and V02 by V01 is A02. So now this is GM2 into R02. So this is minus GM1 into R01. So what is this? V02 by V in, which is with open circuited load. So I'll call it as A0 cascode. A0 cascode. So A0 cascode is minus GM1 R01 into GM2 R02. So this is A0 cascode. A0 cascode. That's what is A0 cascode. So what is R out of this? If you find what is the resistance looking down here, you can see now this is a M2 transistor with you're looking into the drain, but the source is connected with this. So if you find the R out of this, that is this resistance looking down is R02 plus R01 into 1 plus GM2 R0. So this is the resistance looking down here. So having found out what is R out of this cascode amplifier and what is the open circuited intrinsic gain, I can write the block diagram of the cascode amplifier with R in. This is plus minus. So this is like, okay, V in. So this is R out. This is A0 into V in. This is like R in. So this is V0. This is my load. So this is for any amplifier. For cascode amplifier, R in, this is for specifically cascode amplifier. R in is infinity, because if you can see here, this is an infinite resistance, infinity. So what is A0 of cascode? A0 of cascode is minus GM1 R01 into GM2 R02. So what is R out? R out is nothing but R02 plus R01 into 1 plus GM2 R02. This can be approximately written as GM2 R02 R01, because I can neglect this and this. So ultimately it's the product of R01 GM2 R02. This will also call it as A0 into R0. A0 into R, because this happens to be the A0, the intrinsic gain of an amplifier. Fine. So this is a cascode amplifier. Now we can start connecting different loads here. It can be a resistive load, it can be a R0 load, or it can be a A0 R0 load. The loads can be different. Either you can use this load, use this load, use this load. So now what is AV of a cascode amplifier? It is nothing but A0 into RL divided by RL plus R out. What is this? Of course, this is A0 of cascode. A0 of cascode. So A0 of cascode multiplied by load resistance divided by RL plus R out is my AV of the cascode amplifier. Meaning I can have different varieties of cascode amplifier. I can think of having, this is my resistive load cascode amplifier. I'll ground it. This is V in, VB, this is VED, V0, M1, M2, this is RD, and it can be a cascode amplifier with R0 load. You can see this is M1, M2, V0, this is M3, this is VDD. You're connecting some bias voltage. Let me say it as VB1, VB2, and this V in here. This is NMOS, this is also NMOS. And the other one is cascode amplifier with cascode load. This is grounded. This is this. This is PMOS, PMOS, NMOS, NMOS, M1, M2, M3, M4. We did here. This is VB1, VB2. Just name it as some number. This is Vin. Here you measure, of course, writing where you're taking output, where you are applying the input is important. And in all these cases, A naught of Cascode, A naught of Cascode is minus GM1 R01 into GM2 R02. What is R out? R out is, okay, now this is what you're looking down. Okay, what is, suppose if I say this as R down. So what is R down? R down is R02 plus R0. Okay, let me just write it as per this. So now what is AV of the first circuit? Suppose if you want to write what is AV of this. AV of this is, as per this, is Cascode. A naught Cascode is minus GM1 R01 GM2 R02. What is RL? RL is now RD divided by, so what is R out? R out is this. R out is actually this resistance, which is nothing but resistance looking into this what we named it as R out. So this is what is R out. So resistance looking down here, how much is that? So that is now given by resistance looking down is R02 plus R01 into 1 plus GM2 R02. This is R out plus RD plus RD. So then this is for the first circuit. This is for the first circuit. This is for the first circuit. So for the first circuit it is this. For the second circuit, this will go off. This will go off. You'll write it as R03, R03. This is for the second circuit. This is for the second circuit. Rest of the thing remains same. Instead of RD here, you are writing it as R03, R03 because the resistance looking up is R03. Suppose if you consider the third circuit, then this will also be not there. So then what will be multiplied? You'll be multiplying it by R03 plus R04 into 1 plus GM3 R03. What is this? So you'll not neither use RD, neither use R03, but you'll use this resistance, which is nothing but R03 plus R04 1 plus GM3 R0. So this is for the third case. This is for the third case. That's all. So that's what is AV of the Cascode. AV of the Cascode, whether you use a resistive load, this is RD load, this is R0 load, this is like A0 R0 load. This is a Cascode load. Cascode load. Cascode amplifier with Cascode load, Cascode amplifier with R0 load, Cascode amplifier with resistive load. That's it. So what is the resistance looking here is RD in parallel with this resistance. That resistance is actually this. This is that resistance. RD in parallel with R02 plus R01. Of course, it is like approximately connected as R01 GM2 R02. So what is this here? The resistance looking here is R03 in parallel with R01 GM2 R0 approximately. So this is an approximate parameter. If you want to have the exact expression, you have to write this. So what are the resistance looking from here? It's actually what is the resistance looking up? It's approximately R03 into R04 into GM3 R03 in parallel with R01 into GM2 R0. So this is what is the resistance. The R out, the overall R out. So this R out, whatever I have written here, so this R out is for only this, only for the intrinsic amplifier. Of course, without connecting the load. This is with connecting the load. With connecting the load, this is your R out. Hope okay. With this you can able to understand all the amplifiers. Thank you.